So, what we saw is that the work is given as 1W2 or W12 and its integral of V1 to V2 of some P times dV. Over here I am using the capital V again. I could also write it as 1W2 is integral of P d small v. Both of them are essentially the same thing for a system where the mass is fixed. So, what we can try to see is, can we find out expressions for this work when the system undergoes various processes. So, we can integrate this. This is like, for example, some curve integral of y dx. So, in order to integrate this, we need to know the functional form of y in terms of x. We can integrate this if y is a constant, or if y is a function of x, we need to know what is the functional form of y in terms of x, only then we can integrate it. So, we can try to see what are some common processes. The process can be anything at all. As I drew earlier, it can be some arbitrarily shaped thing where we do not know what it is unless we go through the entire process. But there are at least certain processes which are quite common. So, we can try to see what are those. So, we have again, let us look at say the PV diagram itself. Let me for the moment draw capital V. Does not in this particular case it does not matter. So, this line over here represents a process where the pressure is not changing. So, the pressure here is this whatever is the value on this axis. It is not changed. Let us say this is volume V1, this is volume V2, then there are a lot of volumes in between. The value is the same at V1, the value is the same at V2, the value is the same at everywhere else. So, we see that the pressure is not changing. So, this is a process where the pressure is constant, where C is some constant. This line represents a process where we see that the volume here is some, let us say some V3. When the pressure was some P1, the volume was V3. When the pressure is some P2, the volume is still V3. When the pressure is some other value P3, the volume is still V3 and so on. So, we see that the volume is not changing at all. So, this would be for us the line which represents a constant volume process where the volume is constant. Of course, I could have any number of constant volume processes parallel to this. I could also have any number of constant pressure processes parallel to this and so on. One of the other processes which we are commonly interested in is what is called as an isothermal process. We will look at what is an ideal gas in some time, but all of you are sort of familiar with the ideal gas equation of state, and we will, I do not want to write that for the moment, but for an ideal gas that is represented as some PV is equal to constant. So, we know from whatever geometry we had that a curve of the form xy equal to constant represents rectangular hyperbola. So, PV equal to constant on a PV on a, this is on a y versus x axis. So, on a p versus v axis, this must also be something like a hyperbola. Okay. So, what we see is that this green curve for us represents something of that kind. So, this is PV equal to constant, which would be an isothermal process for an ideal gas. We are also interested with other processes which we cannot represent in any of these. So, one of the ways in which we represent some process of that kind is by the equation PV to the power n equal to constant. One special case of this process would be where n is equal to gamma, which is the ratio of the specific heats. We are also familiar with that from earlier. So, equation of the form PV equal to gamma equal to constant for an ideal gas represents an adiabatic process. So, and gamma is greater than, so for example, all of these other processes can be thought of as special cases of this general process PV to the power n equal to constant. So, I am going to for the time being represent this as some PV to the power n equal to constant, and what we see is if n is equal to gamma, we get the adiabatic process. But I can also draw some other process, for example, some process like this, which is also PV to the power n with some other value of n. So, I can have all of these processes. But in general, I can represent all of these processes by PV to the power n. So, PV to the power n equal to constant is what we call as a polytropic process. So, if I put n is equal to 1, then I get this expression, and this polytropic process becomes our familiar isothermal process. If I put n is equal to 0, then this term becomes 1, anything to the power 0 is 1. So, this becomes p equal to constant. So, n is equal to 0 gives our familiar isobaric process. So, from this we have got, by putting n equal to 0 we got the isobaric process, by putting n equal to 1 we got the isothermal process, by putting n equal to gamma we get the adiabatic process, and what I can also do is write p equal to c by v to the power n, and by putting n is equal to plus or minus infinity, what I see is I get the volume equal to constant process. So, this is again the polytropic process with n, which gives us a volume equal to constant process, what we write as an isochoric process. So, what we see is that using this expression we can get all of the processes we are familiar with for having different values of n. What we would like to do now is to calculate the values of work for each of these processes. So, for example, we can start with the isobaric process, which is possibly the easiest to calculate the work for. So, what we are trying to do is find out value of work between some point 1 and 2, which we know is integral from volume going from 1 to 2 integral of p dv. This is the expression we had and we are going to calculate it. So, if we take for example an isobaric process, the equation of this process is that p is constant. So, now I want to find out integral v1 to v2 p dv where p is a constant. So, since it is a constant I can take it out of the integral. So, for the isobaric process I get this as p into integral of v1 to v2 dv, since p is a constant. Okay. So, since p is a constant we can call it anything k or m or l or whatever, it is no longer something which is changing, therefore, we can take it out of the integral, and now we just have integral of dv. So, integral of dv is essentially v2 minus v1. So, what we get is that this expression is p into v2 minus v1 for an isobaric process. We need to remember that this is only true when p is constant, okay, only for an isobaric process. Now, we can look at it for an isochoric process. An isochoric process is a constant volume process or where V is constant. So, we again see that the work done is given as integral V1 to V2 p dv, which is what we had earlier also. But in this case V is constant. So, the volume is not changing. Since the volume is not changing, the change in the volume is 0, because volume is not changing at all. So, if V1 is the same as V2, so V2 minus V1 or change in volume or any differential change in volume, any small change in volume, all of them are essentially 0, because there is no change in volume. So, essentially this term is 0. So, this term into this is also 0, the entire thing is 0. So, what we see is 1 W2 is 0, which is what we get for volume equal to constant process. We can do the same exercise for the other processes we have. So, we can do it for an isothermal process. So, which is of the form P v equal to constant. So, we start off with the same point again. So, we have 1 W2 is integral of V1 to V2 P dV. So, we need to find out in all of these P we need to have it in all in terms of one variable. So, we can either eliminate P or we can eliminate V. Since there are 3 times V here, V1, V2 and V, and only one P here, let us eliminate the P. So, from this expression we see that P equal to C by V, where C is some constant. So, we are going to substitute that in this. So, this gives us integral V1 to V2 C by V dV, okay, where C is a constant. So, I can take the constant out, it is integral of C into V1 to V2 dV by V. So, integral of 1 by V dV is ln V. So, what I get is C into ln V2 minus ln V1, and log of V2 minus log of V2 V1 is essentially C into ln V2 by V1, where the C is a constant, but this constant from here is PV. So, I can put it as PV here, but PV is a constant means that P1 V1 will also be equal to that, will also be equal to P2 V2, will also be equal to some P3 V3 and so on, because all of them are constant. So, I can replace this constant by either P1 V1 or P2 V2, any of them, they are all the same. So, I can for example write it in this fashion. So, I have the expression also for an isothermal process. What would be interesting to do is to do this for the general process. So, let us look at our polytropic process. Where I have PV to the power n equal to constant. So, the work done we know from the previous expressions is integral from V1 to V2 P dV. What we need to do now is replace this P here, so that everything is in terms of the same variable, so that we can integrate. So, from this expression I have P is equal to C by V to the power n. So, this gives me so C is again a constant, so I can take C outside. So, I have this integral. Let me write this as V power minus n. Okay. So, the integral for V power minus 1 minus n is essentially V power minus n plus 1 divided by minus n plus 1. This goes from V1 to V2. So, I have this. So, I have over here this is C into V to the power minus n plus 1 minus V1 power minus n plus 1 divided by minus n plus 1. I can write it in this fashion. So, this also I can write as 1 minus n. This C I can replace in terms of this. So, I had here that PV to the power n is equal to constant, which means P1 V1 to the power n is equal to constant is equal to P2 V2 to the power n is equal to P3 V3 to the power n and so on. So, in this case, so what I can do is I can take the C inside. So, I have this. So, for this constant C, I am going to replace it by this term. For this constant C, I am going to replace it by this term. So, what I get is that this is P2 V2 to the power n into V to the power 1 minus n minus P1 V1 power n into V1 power 1 minus n divided by 1 minus n. So, this is 1 W2, which gives me 1 W2 is P2. So, I have V to the power n into V to the power 1 minus n. So, that is V to the power 1 plus n minus n, which is essentially V2. In a similar way, I have this term, or I can also write this if I want to. N is usually for s greater than 1. So, what I would prefer to write is to write it in this fashion, which is a general expression for the polytropic work done. So, what we can see is, if I was looking at an adiabatic process, then n is equal to gamma. So, the work done would essentially be the same expression with n replaced by gamma that I could get. Similarly, if I was to look at, say, a constant pressure process, then P1 is equal to P2, that comes out, and I have n is equal to 0. So, I would get back this previous expression, which is that the work is P into V2 minus V1. Similarly, if I was going to look at an isochoric process, I would get back the previous expression that the work is 0. So, we see thus that we have expressions for various displacement work processes which are quasi-static. So, we will now keep this expression in mind, and then we will continue in the next lecture. Thank you.